All right, let's look at some examples of solving logarithmic equations. Now, again, it's important to be able to recognize when you are dealing with a logarithmic equation. And in this case, this is a logarithmic equation because our variable x is located inside of the logarithm. All right, so let's get started. Here we have the natural log of the square root of x minus 8 is equal to 5. Now, you might recall from previous sections of the chapter that we could always rewrite square roots as fractional exponents. And so this would be the same thing as the natural log of x minus 8 raised to the 1/2 power. Well, why do we like that? This actually allows me to use the power property for logarithms, and I can bring this 1/2 exponent to the front of my log as a constant multiple. This gives me 1/2 times the natural log of x minus 8 is equal to 5. Now, we can do some algebra here to isolate our logarithm. We want to get the log on its own on one side of the equation. To do that, I can divide both sides by 1/2 because division is the inverse operation of multiplication. Dividing by a half is the same as multiplying by 2, and that gives us the natural log of x minus 8 is equal to 10. So now that we have our logarithm isolated, we can now do the inverse operation of logging, right? Here we're taking a natural log of this quantity. Our variable is located inside of that log. We need to undo that logging, and the inverse operation of logging is exponentiation. Remember, exponentiation just means to make an exponent. I'm going to make each side of this equation an exponent, and the base that I choose for the exponent is going to be the base of the log. Now, because this is a natural log here, this means log base e. I want to choose e as the base of my exponent when I do my exponentiation. This leaves me with e to the natural log of x minus 8 is equal to e raised to the 10th power. Now, again, exponentiation, that just means to make an exponent, right? I made the whole left-hand side an exponent, and I made the whole right-hand side an exponent. Again, not breaking any rules of algebra. If I do it to the left-hand side, I have to do it to the right-hand side. So, because these are inverse operations of each other, exponentiating a natural log with a base of e, those are going to cancel out, leaving me with x minus 8 on the left-hand side of the equation is equal to e to the 10th power. And finally, to solve for x, I need to add 8 to both sides of the equation. X is equal to e to the 10th power plus 8. Now, another way that you could go about solving this exact same problem is to recognize that, yes, in the first step here, we also already have this logarithm isolated. And so we could actually begin this problem by exponentiating both sides with the base of e. This would be e raised to the natural log of the square root of x minus 8 is equal to e to the 5th power. Now, because these are inverse operations of each other, exponentiating a log, I'm going to end up with the square root of x minus 8 is equal to e to the 5th power. To solve for x, now I need to continue to do inverse operations. Well, the inverse operation of taking a square root is to square. I can square both sides of the equation. That gives me x minus 8 is equal to e to the 5th squared. And remember that when we have exponents raised to exponents, we're going to multiply the exponents. This gives me e to the 10th power. And to do the inverse operation of subtracting 8, I would have to add 8 to both sides, giving me x is equal to e to the 10th power plus 8. So, two different ways to solve the exact same equation, giving us the exact same answer. Remember, if we abide by the rules of algebra, we're still going to get the correct solution. All right, let's look at another one here. 2 minus 4 log base 3 of x minus 1 is equal to 10. Again, if we have a single logarithm, we want to try to isolate this log on one side of the equation. Get it on its own. Well, what algebra are we going to have to do to isolate the log? We would begin by subtracting 2 from both sides of the equation. That gives me negative 4 log base 3 of x minus 1 is equal to 8. Then, because this negative 4 and this log are connected by multiplication, I can divide both sides by negative 4. Again, division is the inverse operation of multiplication. This gives me log base 3 of x minus 1 is equal to negative 2. Now that we have isolated the log, we need to do the inverse operation of logging. Again, notice our variable is being logged. Well, the inverse operation of logging is exponentiation. That means we need to make each side of the equation an exponent. And what are we going to choose as the base of our exponent? 3, because that is the base of the log. We have 3 raised to the log base 3 of x minus 1 is equal to 3 to the negative 2. Because these are inverse operations here on the left-hand side, the whole left-hand side of the equation is going to become x minus 1. And 3 raised to the negative 2, well, those negative exponents give us a reciprocal. That's 1 over 3 squared, which is 1/9. X minus 1 is equal to 1/9. We can solve for x by adding 1 to both sides of the equation. Adding 1 or adding 9 over 9 gives us x is equal to 10 over 9 for our final answer. All right, a couple other ones here. Solve the following logarithmic equations. Log base 3 of x plus 1 plus log base 3 of x plus 5 is equal to 1. Now, we said before that our goal is to try to isolate the logarithmic quantity. However, in this case, we have two separate logarithms. But notice that they have the same base, and they are also connected by addition. Think back to some of our properties of logarithms that we covered back in section 3.3. Yes, we could actually combine these into a single logarithm. Okay, addition of logs with same bases condenses into a single log when we multiply the quantities inside of the log. So I can rewrite this whole left-hand side of the equation as log base 3 of x squared minus 8x plus 15 is equal to 1. Right? This x squared minus 8x plus 15, that's what I get when I FOIL out x plus 3 times x plus 5. Right? X times x gives me x squared. I get a plus 5x, a plus 3x gives me a plus 8x, and 3 times 5 gives me 15. So now I have a single logarithm isolated on one side of the equation. Now I can exponentiate both sides of the equation. All right? Again, I can only exponentiate if I have a single logarithm on both sides. So here I have log base 3 of x squared plus 8x plus 15 equals 1. I need to undo this logging by exponentiating with a base of 3. Again, always pick the same base as the base of the log. This gives us 3 raised to the log base 3 of x squared plus 8x plus 15 is equal to 3 to the first power. Again, exponentiate means make an exponent. I make this whole left-hand side an exponent. I make this whole right-hand side an exponent. Well, because these are inverse operations of each other, exponentiating this log is going to cancel out that operation, leaving us with x squared plus 8x plus 15 on the left side is equal to 3. Yes, 3 to the first power is 3. Notice that this generated a quadratic equation. And how do we solve quadratics? We set them equal to 0. We're going to subtract 3 from both sides, and we are going to factor x squared plus 8x plus 12. That is going to factor into x plus 2 times x plus 6 is equal to 0, leaving us with x equals negative 2 and x is equal to negative 6. Now, one thing to keep in mind here. Notice that in the first step of this problem, when we combine these two logarithms, we ended up multiplying variables x. Okay? We ended up multiplying by variables. Anytime you multiply by variables, you have the possibility of introducing extraneous solutions, or solutions to your end equation that are not necessarily solutions to your original equation. So anytime we multiply by variables, we want to check to see if we have any extraneous solutions. Make sure you plug each of these into the original equation and make sure that they work out. Okay, notice plugging in negative 2. That gives me log base 3 of negative 2 plus 3 is 1. Log base 3 of 1 plus log base 3 of 3. Well, log base 3 of 1, that would be 0. plus log base 3 of 3 would be 1 is equal to 1, right? Our first solution checks out. If I plug in -6, however, that gives me log base 3 of -3. And hopefully you recall from our first section on logarithms that we cannot have negatives inside of a log, all right? The domain of our logarithmic functions is only going to be values that are greater than 0. All right, we can't have 0 or a negative inside of a log. Therefore, x equals -6 is an extraneous solution. We can cancel that one out and recognize x equals -2 is our only answer. Again, check for extraneous solutions when multiplying by variables. Okay, if we multiply by an x, we have the chance of introducing an extra solution. All right, and we cannot have negative values or zeros inside of a log. All right, let's try another one here. The natural log of x plus 1 minus the natural log of x minus 2 is equal to the natural log of x. Now, we cannot just exponentiate each of these individual quantities. All right, there is no distributive property for exponentiation. You can only exponentiate if you have a single logarithm. You must exponentiate an entire side. So instead, we can use our properties of logarithms to condense this into a single log. Notice I have two logs with the same base connected by subtraction. Well, we can combine those into a single log by taking the quotient of x plus 1 and x minus 2 inside of the log. The natural log of x plus 1 divided by x minus 2 is equal to the natural log of x. At this point, we could exponentiate both sides of the equation with the base of e, because that would undo this natural log, or we can use the one-to-one property. Notice that we have two logs with the same base set equal to each other. Therefore, the quantities inside of the logs must be equal. X plus 1 divided by x minus 2 has to equal x. So let's now solve for x. To do so, we must get rid of this fraction. Multiply both sides of the equation by x minus 2. This gives me x plus 1 is equal to x squared minus 2x. And again, we have generated a quadratic equation. Generated a quadratic equation to solve quadratics. We set them equal to 0, and we are going to factor them. So let's subtract x and subtract 1. Doing so gives me 0 is equal to x squared minus 3x minus 1. Now, this is certainly not factorable, so instead we need to use the quadratic formula. Yes, x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. This leaves me with x is equal to 3 plus or minus the square root of 9 minus 4 times 1 times negative 1, all divided by 2. Continuing to simplify, we get 3 plus or minus root 13 over 2. Now, you might think, we have two solutions here. But what did we do to go from this fraction to this quadratic equation? Again, we multiplied by a variable. And what do we have to check for when we multiply by variables? Extraneous solutions. All right, remember, we can't have negatives or a 0 inside of a log. So I have 3 plus or minus root 13, all divided by 2. Well, subtracting root 13 is going to give me a negative number, right? Root 13, well, root 9 is equal to 3, and root 16 is equal to 4. Therefore, root 13 has to be between 3 and 4. That's going to give me a negative. And if I try to plug a negative in here, right, I'm going to get a negative and a negative inside of this log. So the 3 minus root 13 over 2 cannot be a solution, meaning we only have one answer, 3 plus root 13 divided by 2. All right. The other one would give me a negative inside of a log, and we must make sure we check for those extraneous solutions.